This is lesson 2-2 from activity 2. It's talking about deductive reasoning. Now, the activity before it's how there's not videos for it, but I do want to review page 13 really quickly. The book does a great job of introducing inductive reasoning, what it is, how it leads to a conjecture. It does a great job of giving you a real-world example. That's item 1. And we use inductive reasoning all the time. A lot of our decisions that we make daily are based off of inductive reasoning. If we see some sort of pattern, then we're going to alter our actions or alter our schedule to avoid things, whether that's driving, and so you notice that there's a pattern of heavy traffic, so you'll adjust your route to work or to school, or your parents may do this, and so they see some pattern, so they use inductive reasoning. They make a conjecture and say, hey, this is going to happen again, so let's decide to do this instead. So 1 was a great example of a real-world application of inductive reasoning, and then 2, parts A through D, were some great series and sequences. Here on A, there was letters and numbers, so I loved that one. That was a great example. So you had the consecutive letters alternate with multiples of 4. That was one way of looking at it. Part B, this was powers of 3. Part C, the difference between the consecutive terms increased by 2 each time. So you start with the number 3 and then add the consecutive odd numbers. So you start with 3 and then add 5, then add 7, and then add 9 and 11, 13, so on and so forth. And D is one of my favorite series or sequences of numbers, and that is the Fibonacci. It is found all throughout nature, and it's just a really cool sequence, and there's a bunch of videos out there that discuss it and its importance and the golden ratio, and it gets pretty complex but pretty awesome. So the book does a great job of introducing what inductive reasoning is. It has this extremely long activity where you fill out this and you say how many non-overlapping regions, and there's 2 in this and 4 in this one and 8 in this and 16 and so on and so forth. It says, well, what do you think would be next? And we said, well, 32, because we're just doubling it apparently, and our conjecture was wrong, because the number of unshaded regions formed by the 6 points was 31. It says, well, was that the number you predicted? And we said, no, it wasn't. That's okay. Our conjecture was wrong. Well, what do we do? We go back to the drawing board, we collect some more data, and you come up with a new conjecture, a new educated guess, and from there you'll continue testing it. Well, today what we're going to talk about is how do we take one of those conjectures, an educated guess, a generalization from inductive reasoning, how do we take that and then prove that it must be true without a doubt? And so that leads us into deductive reasoning. So once again, this is page 18, lesson 2-2, talking about deductive reasoning. So up at the top, our learning targets are to use deductive reasoning to prove that a conjecture is true. So we're going to come up with 3 conjectures, and we're going to use different methods on trying to prove those conjectures to be true, and not only true for the some examples and observed data, but beyond that observed data. And then also we're going to develop geometric and algebraic arguments based on deductive reasoning. So we're going to look at some integers, and we're going to talk about how they act under the operation of an addition, how even and odd integers do. So first off, let's talk about what an integer is. So over in my notes, let's just define an integer. An integer, it's a number that can be written without a fractional component. It's pretty much what we got here are the whole numbers. No fractions, no decimals, no irrational numbers. We're talking about the whole numbers. Not only just the whole numbers, but or not only the positive, but we're going to include negative. So if you want to make a point that these are positive and negative, we're talking about the positive and negative whole numbers, and then also this includes 0. So this is what we're talking about when we say the set of integers. It's a bunch of numbers that can be written without a fractional component, so that's a big fancy way of saying whole numbers. It's the positive and the negative, and we do include 0. So this is the set of integers. Now, before I go much further, I want to introduce this topic of closure, because integers is a set. It's a set of numbers, and even though there's infinitely many members in this set, there's still closure to it. And what I mean by closure is if you flip over to page 20, you're going to see this math tip off to the side. And it says a set has closure. So a set meaning like a set of numbers. It has closure under an operation. By that it means like a mathematical operation, addition, subtraction, multiplication, division, and so on and so forth. It has closure under an operation if the result of the operation on members of the set is also in the same set. So I'll feed you, baby birds. Check this out. So what we're saying is we've got this huge set of integers, right? So I'm going to pull an integer out of here. We'll call it I1. If we have this first integer, I sub 1, and we have a second integer that we just pull out, well, if we do some sort of mathematical operation on these two members of this set, for instance, if we add these together, because that's a mathematical operation, what's going to happen? What's going to be the solution when we add these two values, or whenever we perform this operation? Well, if that solution, or if that number, whatever it is, if that 2 is in the set where we got these original numbers from, then that means it has closure. So let's just think about this. You can pick any two integers you want. So I1 and I2 can be any two whole, positive, or negative numbers. It can also be 0 if you want. So choose any two integers. What we're saying is when you add those two integers up, you're just going to get another integer. That's the only thing that can happen. You can't add two whole numbers, whether they're positive or negative, and get some fraction or get some decimal or get some irrational number. No, when you have wholes and you add them up, you're just going to have more wholes. So when you add two integers together, the sum will always be another integer. And when that happens, that means that the set has closure over that mathematical operation. So what we're going to write here is that the set of integers has closure over addition. The set of integers has closure over addition. Or, I guess a better way of writing that is not over, but under this mathematical operation, addition. So the set of integers has closure under addition, meaning when you take any two integers and you add it up, it's going to produce another integer. Just real quick side note, a mathematical operation that does not have closure when you're talking about integers is division, right? So take like 3 divided by 2. Well, 3/2 is not an integer. So this number would not be in the set of integers. Therefore, there is not closure under the mathematical operation division. But all we're going to be concerned about is addition for today in integers. Another quick side note that I wanted to talk about is the distributive property in factoring. Make sure that you understand. So let's say I have this expression. I'm sure that we're all pretty familiar with the distributive property. So we have 2 times the quantity 8x minus 6, I don't know, plus 2. So the distributive property, we take this coefficient that's in front of the set of parentheses, in front of this quantity, and we multiply it to each term that is inside the set of parentheses. So when I distribute this 2 to each term inside of the parentheses, I will get 16x minus 12 plus 4. I'm sure we're all really comfortable with that. We feel good about that aspect of the distributive property. But also there's another side to it where you can factor out things that these terms have in common. So if I wanted to, I could rewrite this expression as 4 times the quantity 4x minus 3 plus 1. And so what I've done is kind of like the reverse, and I've factored out a 4 because every single one of those terms had a 4 as one of its factors. So all three of these expressions are conveying the same exact thing. They're just represented a little differently. You need to be comfortable with these, being able to go to distribute a number to get rid of the parentheses and also to factor out. You need to be comfortable flowing back and forth. It also works when you have variables. So these two terms, they not only have a 7 in common, but they also have an x in common. So if I were to factor out that 7x, I would get 7x times the quantity x plus 2. So be aware it works with variables as well. So hopefully it's not new, but I'm just trying to remind you that we are allowed to factor things out of expressions. So having talked about integers and defining that set of numbers, positive and negative whole numbers including 0, talking about that under addition, integers is a closed set, so there's closure with that. And then also distributive property, I think we should be, finally, after 13 minutes in, I think we should be good to go. But this is just very important that you understand how we got here, talking about inductive reasoning and talking about coming up with a conjecture and then taking that conjecture and using deductive reasoning to prove it. So here we go. It says, in this activity, you have described patterns and made conjectures about how these patterns would extend beyond your observed cases based on a collected data. So we've done that before. We made a lot of conjectures about some patterns. Some of them are right, some of them are wrong. That's exactly what it says next. It says some of your conjectures were probably shown to be untrue when additional data were collected. So that was that whole chords in the circle and non-overlapping regions. We made a prediction, we were wrong. That's okay. There's not a glitch in the matrix. Life isn't over. It's fine if we make a wrong conjecture. It's cool. We just have to go back to the drawing board, collect more data, and come up with another conjecture. Then it said other conjectures took on a greater sense of certainty as more confirming data were collected. And so I think that as we tested some patterns out, it solidified your educated guess, your conjecture of what the pattern was, and making decisions based off of that. So now we're going to take these conjectures and see when are they always true beyond that observed case.